Hi, my name is Tiffany Fugate, and today we're going to be um, paper folding to create conic sections, and we're going to simulate that today using Geogebra. So what you should see now is my geogebra.org account, and I've signed in using my Google account. So there's my name, Tiffany Fugate. And all I'm going to do is I'm going to go to where it says new here. I'm going to click on new and I'm going to select GeoGebra Math Calculators. This will take us to the old version of GeoGebra that so many of us are used to. Okay, so once I get there, the default settings have the grid lines and the axes set up for us. And in order to do geometric constructions, we normally don't want those there. So I'm going to turn those off. Um, there is a menu here in the corner that says toggle sidebar right here. So I'm going to click on that. I'm going to turn the grid lines off by clicking, and then I'm sorry, the axes off, and then I'm going to turn the grid lines. I'm going to select the blank, and so now I have a blank canvas. Okay, so the first conic section that I'm going to simulate is the parabola, and a parabola is defined to be the set of points in a plane that are equidistant from a fixed point called the focus and a fixed line called the directrix in the same or a parallel plane. So typically we would use patty paper during this activity, and we would draw a straight line and a fixed point not on the line. So we're going to do the exact same thing here in GeoGebra. So I'm going to go up here. I'm going to grab me a line, and I'm going to get a point that's not on the line. Okay. Now, we would then begin folding the fixed point onto the line, forming multiple creases, um, and then trace over the crease lines with a pencil, and these creases would then form the tangent lines to the parabola. Well, what you're actually doing is when you fold C onto A, you're actually creating perpendicular bisectors. So what I'm going to do is I'm going to go up here and I'm going to grab my perpendicular bisector tool to form a perpendicular bisector between these 2 points. And obviously one tangent line is not going to help me clearly see my curve. So I'm going to place several points on this line, my directrix, so that I can then uh, make several perpendicular bisectors. Okay, so this is just a matter of getting a lot of points. The more points you have on your line, the better your curve is going to look. So now I'm going back to my perpendicular bisector tool, and every tangent line is going to be a perpendicular bisector between point C, remember that's your focus, and each of these points on your line. And it's pretty clear to see if you've already used one of the points, it'll overlay. So you just kind of keep working your way down the line until you have used every point that you've placed on your line. Now, if your students are doing this with paper, every student is going to place their directrix a different distance away from, I'm sorry, every student's going to place their focus a different distance away from their directrix. So they're all going to generate different parabolas. What's really great about simulating this in GeoGebra is that once you actually have this constructed, then you can grab your pointer tool and then you can grab a hold of this focus and actually show them what happens as the focus gets closer and closer to the directrix. Your parabola would then get stretched vertically. And so as your parabola gets further away from the directrix, um, the parabola shrinks vertically. And it'll also show you, as you go from left to right. So it's a lot more interactive than just simply folding it with paper. So that's the parabola construction. Now we're going to move on and look at the ellipse. So I don't really need this for anything anymore. So I'm just going to, let's see, come over here to these three lines. And generally on any Google product, which GeoGebra is kind of integrated with Google, anytime you see three lines, that means that there are more options available for you. I'm going to go over here and I'm going to click New. And I don't really care about saving this, but if you want to save this, Parabola would probably be a pretty reasonable name to select. Save that. Now I've got a new blank document. Okay, so the ellipse. An ellipse is defined to be a curve that is the locus of all points in the plane, the sum of whose distances from two fixed points, called the foci, is constant. The elongation of the ellipse is represented by its eccentricity, which ranges anywhere from 0, which would be a circle, to a 1. So on your patty paper, you would draw a circle and a fixed point in the interior of your circle. So we're going to simulate that here. So we're going to start with a circle. Doesn't really matter which way you choose, but here's my circle. And then I need a point in the interior. Okay, so I'm just going to put it here. Doesn't matter where you put it, just so long as it's inside the circle. And once again, if I'm going to need points on the circle, because the next step would be to begin folding the fixed point C, onto the points on the circle. Okay, so if I'm going to fold point C onto point B to form tangent lines of the ellipse, then those once again will be perpendicular bisectors. So C on to B, that would be one tangent line of your ellipse. All right. So just like we did before, I'm going to want to put a lot of points on this circle, because the more points I have, the clearer my curve becomes. Okay, so now go ahead and fill in with your perpendicular bisectors. See, we started with B, so I'm just going to go around the circle here, putting in my perpendicular bisectors to start forming my curve. So you can kind of already see that ellipse starting to form. And it's already pretty clear with all those tangent lines that we've got. We could probably, yeah, I think that's it. Okay, so now we've got that form. So could start to ask our students a few questions now. Like we did before, we could take our pointer tool and grab a hold of C, which was our focus. Um, First of all, what is the relevance of point A? That would be a great question to ask students. Well, it turns out that point A, which was the original center of our circle, happens to be the other focus of the ellipse, which is interesting. So um, if you take C and move it closer and closer to A, then you just get your circle back. So as C gets closer and closer to A, the eccentricity of your ellipse gets closer and closer to 0. As C moves further and further away, the eccentricity gets closer and closer to 1. What do you think would happen as C is on the circle? What do you think would happen if C was to move outside the circle? And that kind of moves us to our next activity. Okay, don't throw this one away because there's no use in reproducing. Um, the hyperbola actually is defined to be the locus of all points such that the difference between the distances to each of two fixed points is constant. So on your patty paper, you would draw a circle and a fixed point in the exterior of your circle. So let's not work so hard to reproduce this. Let's just take C and move it outside the circle. So let's find out what happens when we move C outside the circle. So when C moves outside the circle, we actually get the branches of the hyperbola. Okay. Um, so there are the three conic sections. Uh, you can do these with patty paper, folding to get your tangent lines that form your curves, or you can simulate that in GeoGebra as I've just done. We can also prove that each of these work using simple geometry triangle congruence proofs. If you'd like more information on that, just put it in the comment section and don't forget to like and subscribe. Thanks, y'all have a great day.